Surfaces represent phenomena that have values at every point across their extent. This is like theory. Someone will say he's just reading this to us, but I'm not just reading it to you. I know this is true. Okay, it falls under 3D analysis and surface renderings. So what are we saying? What we are saying is this: anytime you say a surface, say table surface, floor surface, gravel surface. This is the definition that fits it. A phenomenon that have at every point, you have a value at every point of that phenomenon. Okay, so this surface, this table that I'm hitting right now, I don't know if you can hear the sound of it. The surface of the table is phenomenal. In other words, at every point on it, there's a certain value. And what's that value? I will find that there's a wooden material, okay, which is probably polished, all right, and has a certain color. Are you okay? Once I drop off this table surface, I'm falling off. That's it. Okay, let's look at water surface. Water is a surface. If you are really you are cruising, you are surfing water, you are on the surface of water. Are you with me? At every point, you will find a value. What's that value? You find water, water molecules there. If you are on a bare soil, everywhere you are, there's some soil. So you can find a location and then you can find a value. That is how surfaces work. Please, what I just said now is a secret to everything else I'm going to talk about. At every point, okay, across the extent of this phenomenon, you will find a value. That's it. When you have that situation, you have a surface. All right. But then growing up, we've all learned it. Surface, your table surface, one surface. You use the word surface. Okay. The one I said actually is chi, and it means like whatever. Okay. So you have to understand that you know this already. But let's take it a bit higher. Are you okay? Let's try and understand this better. In fact, you know it. You know what surfaces are. The values at the infinite number of points across the surface are derived from a limited set of sample values. In other words, when you take a surface, the values are continuous. They never cut off. When you take any surface, so when you are on a surface, you are on it until you actually come off it. You are actually on it. And the number of points that define the surface are infinite. So in maths, when we say finite, a finite set of values, it means that you can have a limit to it. Okay? In other words, it cuts off at a point. But with an infinite number, it means like a lot, plenty. I mean, like I'm tempted to use that word. Of points. In other words, if you say I'm on a water surface, then you can have like 1,000 points of water, 1,000,000 points of water. In fact, as you go across the surface, you find out that they are even, and that's why he's saying an infinite. Are you okay? Set of points. Are you all right? So an infinite number of points across the surface are derived. What is the why are we deriving? Something. If you say you're a surface, what's the derivation coming from? Straight away, it brings your mind to the fact that I am talking about the reality of surfaces, and I'm talking about the representation of a surface in a computer. Are you okay? Remember, we are talking about GIS. So GIS models our reality, our geographic reality. Okay, so the values that we find at the infinite number of locations are actually being derived from, a sample of points. All this sounds very, theoretical, but we will get there. I'll tell you that what we are talking about is very simple. It's very, very simple. So we say that these limited points may be based on direct measurements. So you want to generate a contour surface. Are you okay? The first thing you do is that you create a grid over the site. And then you pick points at the intersection of the grid. And then when you have done that, you draw a contour line. isn't it? And then once you draw one or two contour lines, you start interpreting the contour to say that I have a mountain, I have a conical hill, I have a valley, I have a pass, I get what I'm saying? You can now describe the geomorphology of the area of interest. Okay, so before you build a house, then the architect will say, let a surveyor go and pick the spot heights for you. That one you did it because you want to build, isn't it? Then a few days later, you've forgotten about it, why the architect asked you to pick those points. He's trying to understand the surface. He's trying to now work with a surface and then to put a design on top of the surface. If you don't understand what you have, you can't build on top of it. Okay, this is by me. It's okay, 2021. If you don't understand what you have, you can't build on top of it. Okay, by me, I said it. All right. So basically, surfaces. The reason I'm not really talking about spot height contours is because that's something you know already. If you've done some surveying, you know about contours. You know about spot height. So it's like, oh, is that what you're talking about? No, I'm talking about surfaces. I'm talking about temperature surfaces. Are you okay? So surfaces go beyond just height values. Surfaces are not just you walking on top of a mountain and walking on a surface. There can be another surface. You can have a surface created from values, and these values are actually not heights. They are actually other values like temperature, 30 degrees Celsius, 50 degrees Celsius. Then you can display it in a computer looking like the surface of a surface, but in this case, it's not. It looks like a mountain, but this mountain is a temperature type. Okay, and the higher the place is raised, the higher the temperature value is. Surfaces, surfaces, and so that is why it's falling under 3D analysis and surface renderings. 3D, yeah, height. 3D is XYZ. So XYZ, that the Z doesn't have to be height, basically. It can be any value. Can be even the dollar value. Are you okay? How much does it cost? There are some places that you go, some shops, some is it restaurants that you go to. Someone told me that in some restaurants, when you go, all you need to do is to pick a plate, and then you are paying 300 Ghana cedis. Nobody asks you to come there. Are you okay? They just don't want people who are broke to come to that restaurant. Are you okay? So we're talking about surfaces here, and it can be any value. It can be the dollar value, it can be temperature value, it can be anything you can think about. Are you all right? That can be measured. And then remember that surfaces are created from sample values, which can be measured directly. Okay, so I can decide that I'm doing a survey. Let me just find out where all the foreigners are in Accra. I go and I pick their locations, and when I finish picking their locations, I will just create a surface from that, and then I'll give a value to every foreigner. Find out that okay, the farther you are from Ghana, I give you a value. I will get a surface from that. That is what I'm talking about. Meanwhile, height values to create a surface for us. So it says this. Let me just take this again. The infinite number of points, say they may be based on direct measurement. The sample points can be based on a direct measurement, such as height values for an elevation surface or temperature values for a temperature surface. I hope now, so I'm kind of reading it for you now. Between these measure location values are assigned to the surface by temperature. Okay, this is what happens. When you have sample values, you can only obtain new values, an infinite number of points from the sample values by interpolating. Okay, so I'll go to the whiteboard if it's still there. I think my whiteboard disappointed me today. It just doesn't want to work today. So it went on holiday. Shame on the whiteboard. It's still not bad.
Is he afraid of the i5 laptop?
It's so much afraid of the i5 laptop, but when it sees the i7, it's going to run away. Exactly. Okay, so I think it's a shame because I think I even used it not too long ago. Did you see it? I used it. Okay, but there's something funny going on. Here it says my screen sharing is paused. New share. Let me see. Okay, so maybe I'm the one who is not handling I updated my Windows, so I think it's having. It said I'm learning. Let me just. I'm learning. So I shouldn't blame the Microsoft whiteboard. It's been updated. All right, guys. Let's move on. Let me show you this one. So how do I create a surface? Watch me. I'm going to do it in the computer. I have to simply give some sample values. From the samples, I'm going to do interpolation. Then that's it. I'll have more values, all right? And then these values are now going to be the surface. Okay. Now what it means is because I'm interpolating, the software by the software can now interpolate and find so many values. Okay, so many values. In fact, it can have millions of values from the interpolation because remember, it's an algorithm. It's not a human being doing it, it's a computer doing it. I gave the computer these red points. Okay, this is what the computer is going to do. Remember that at these points, there are values like 50, 29, 30, 80, 70, okay, 60, 45, 30. Are you with me? Okay, so now the interpolation is done by the software, the GIS software in this case. And this is what it does. Between 29 and then 50, there should be a way of determining the values that fall along this. All right, between any combination of points, we can interpolate and find the values there. So think about it, that between this and this, we can interpolate, between this and that, we can interpolate, between that and that, we can interpolate. And so there are interpolation methods, are you okay, that are used. We have what we call the nearest neighbor, are you okay? There are so many of them. We can use the spline. Okay, we can use bilinear. They are all formulas in mathematical, methods that have been used to determine the value of a thing. Let me give you the basic of interpolation. When you use the line of best fits, okay, in a way you try to determine values based on samples. Okay, all right. So this is what we mean, and we all know how interpolation is done. But I just quickly want to touch. It won't come in any exam of mine, but I want to remind you that if you have 50 here, if you have 100 here, and the distance from here to here is 200, you can determine the distance at this point. Okay, it's very easy and basic mathematics that you can do. You can use similar triangles. You'll be able to do that. So surfaces, there are infinite number of points that can be found across the extent of the particular surface. Are you all right? But then they just didn't come by. They were derived from sample points. Okay? All right. I'll go back to my PowerPoint. Go back to my PDF, So surfaces for you. Let's see this one. Surfaces can also be mathematically derived from other data, such as slope and aspect surfaces derived from elevation data. Yeah. So you can have a slope surface. Okay. A slope surface, on a slope surface, every value you find is telling you the rate of change. Okay. So you know delta y or delta x. Let's not go into all that. You are engineering students. You can relate to what I'm talking about. You have a slope surface. Any point on that surface is telling you how you are falling. Are you okay? How the change of y is doing against, how well it's doing against the change of x. All right. We can have the aspects. The aspect surface then will show you the direction of the slope. I'll talk more about these surfaces. Are you all right? We just want to tell you that a surface doesn't have to be what we know it to be. Okay, it can be different surface. In fact, we can have a political surface. We can create a, someone can just generate a surface that tells you, the way Ghana is in terms of politics by simply getting to know political affiliations from different households. Are you okay? And then now you start working out, creating a surface, and you realize that it looks, Accra will not look the way it's supposed to look anymore. All right, great. Surface of distance from bus stops in a city. Think about how interesting that is. Surface of distance from bus stops in a city. Surfaces showing concentration of criminal activity or probability of lightning strike. So let's talk about the criminal activity. In that case, we're talking about crime hotspots when there's a crime. Are you okay? So you're putting up a project and then you have a hotspot map because the project, the location of the project is supposed to be determined based on maybe safety or maybe it's actually a criminal bureau or something like that. Are you okay? Center for Crime Analysis, something like that. When you put it up, where should we put it? Don't just get up and say there's a piece of land that we found. Are you okay? Close to the sea. Let's go and put it there. You just don't do that. Let's go beyond the basic. All right. Surfaces can be represented using contour. I think here, this is your friend. Embracing. Is that okay? Contour. We all know contour. Contours are lines passing through points of equal height or elevation. All right. Simple. Contours can also be, they are isolines. They are isolines. Okay. Arrays of points. So let me tell you what we are actually saying. We are saying that if it's a surface that you are looking at, then represent it by an array of points. Just have a lot of points, all right? And that's a surface. That's how best you could represent your surface. Or draw lines. Draw lines. Plenty of them, but these lines should be going through points of equal value. That will also give us a surface. Or do one thing, use what we call a triangular or triangulated irregular network. Let me write it down. On purpose, I have to just put this down for you to see what I just said. So TIN stands for triangulated irregular network. Okay, or TIN. So this TIN is what you see a lot of these 3D animations, okay, cartoons, the ones you are watching, Shrek, and all these recent cartoons that we've seen around. All right, Sophia and those things that little children are watching, they are built from this because when you look at them, you realize that no, this cartoon is different from the 1982, 1992, maybe 1992 is too far away, 1995 kind of cartoons. Are you with me? Because they look more realistic. I mean, you can see that this is a solid. Are you with me? So there's a surface. So we're not talking about a kind of cartoon that walks flat. Okay, he's walking this way. It's like as if you wonder what is happening here. All right. So triangular or triangulated irregular network is the short form is TIN or TIN. And we can represent surfaces like that. And in fact, that one is one of the most beautiful. I just love it. I like those surfaces. So contours, I think we talked about that. Need I repeat myself? I don't think so. Contours are sets of line of equal value across the surface. Here, the word height was used, but most of the time we are talking about height values. So points can be regularly, irregularly distributed across the surface. If they are regular, yes, it's preferred. But even when you do contouring as an engineer, contouring that you learned in 7 is really pointing to the fact that you just don't use regular points. You also take points which have interesting variation in height. You have to pick heights there. You don't pick heights regularly. Okay, it's a 20-meter interval. So 20-meter interval is what I'm going to do. Are you okay? You look at areas where there's a dip, there's a sudden change in slope, and you have to pick that one as well. Because there's a disadvantage with using regular, points. Okay. So that is that 10. I think we talked about 10. Ready? Nets of triangular faces. So You will see the cartoon like that, but it's actually made up of triangles. Okay, and then on those triangles, the color that you are seeing, if the cartoon is wearing some black, there's some brown top, yeah, brown top. Then in that case, it's like the faces are colored brown. Are you with me? And then you can almost see that this cartoon is, it seems it's really chesty. It's got some muzzle. Are you okay? It's showing some chest. Are you with me? That protrusion, that rendering of the 3D object is as a result of the use of a triangular irregular network. It is a surface. It is a surface. We'll talk about this. So landforms. So you can represent the whole AITC view area. The wager area seems it has interesting morphology, geomorphology. So can you imagine if you did a 3D model of this place? Then you can say, okay, what if we cut this? If we cut off the AIT part? No, I'm just kidding. All right, so obviously we need to, understand that the computer has a way of representing a surface. It can use points, an array of points. It can use lines, are you okay? Or it can use a raster. So I think the raster is missing in these ones, all right? Okay, so let's move on. Rasters, okay, I want to read this one. I saw the word engineering here so that you will love it more. Tens are usually used to represent terrain surfaces in engineering applications. Tens are usually used, let me highlight it, to represent terrain surfaces in engineering applications as the spot heights can be irregularly, blah, 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 distributed to accommodate areas of high variability in the surface and their values, blah, blah, blah. Okay? All right. So, yeah, let's move on. Rasters. So, when you see raster, anybody hearing the word raster, and this word sounds strange to you, be careful, okay? And try and lead a very humble life. Are you okay? Why am I saying this? Because we have actually talked about rasters in this class, so you are supposed to be familiar with it. Rasters are rectangular arrays of cells or pixels. This is the first time you're hearing this. If it's the first time you're hearing it, you are actually almost in the trouble. Are you okay? All right. And so that's it. Rectangular arrays of cells. We said regular squares of grid cells, we said it's an interesting way, each of which stores a value for the part of the surface it covers. Tessellate an area with regular grid squares. Are you okay? Rectangular arrays. Are you okay? So a square is a type of a rectangle, except that the size is equal. So you can get away with it. A given cell contains a single value. I think we are just describing what rasters are. So something we've already talked about, but I'll still talk about it again. A given cell contains a single value, so the amount of detail that can be represented for the surface is limited to the size of the raster cells. Okay, let me go back to my board, and I want to just elaborate on how these four ways of representing a surface. All right, so I think I have to find a trick how to get this one working. Assume the share. Okay, new share. I think it's my bad, but I have to get used to this. Okay, I get here. Then resume share, new share. Okay, all right, great. I think my software is updated, so I have to get used to the new updates. So there's a surface. What surface is this? It's a temperature surface. Wait, it's a temperature surface. From what we have learned today, this is how the temperatures were obtained. There were actually weather stations where temperatures were picked up or something like that. So at this point, they are weather stations, okay? From what you've learned today, the sample points, surfaces are derived from sample points. Then, so these points are now interpolated, are you okay, to generate more points, all right? So what is our extent? Our extent is the area of interest, okay? All right, what are the other ways that we can represent these? All right, because obviously there are numbers that can be associated with this. Okay, so what do? We create a set of regular points. When we interpolate this, when we interpolate between these points, we can now obtain a regular set of points. Okay, so I can put blue. So if I do regular points, it's possible I can do this. Then I get a grade. So in fact, there's some software, instead of taking a raster data in the form of a picture per se, they take a grid. Can you imagine that? That is explanation. This Zoom session will end in 10 minutes. When it ends, let's use the same link to rejoin. In some software, they take a certain file format, which is called a grid. In other words, what you have actually given it is not your normal picture, which you say rasters have to be. All right, so this is, I couldn't do it well, but let's assume all the blue points are regular. When I say regular is regular, it means the distance between the points are the same. Meanwhile, this has been derived from the red points. Okay, which are the sample points. Okay, now if I decide that, okay, I'm not interested in using an array of points, okay, what are my options? I can say that, okay, I want to draw lines to join points of equal height. Okay, where do I want to start from? A value of 45. Okay, value of 45, I joined by interpolating, I got the 45 points with value 45, which is possible. Okay, then I realized that, okay, the next one, so then you have what we call a contour interval. Will be maybe 55. So the 55, that will also go that way. Then another one. Okay, so now anybody who is really good can tell that, okay, if this is 45, and this is 55, and this is 65, then it means this is actually a dip. We are having a dip in the center, towards the center. We're having it. And that's interesting. It means the peripheries are hotter than the middle. Assume these are temperature values. Why is that so? Then you can pay, spend money based on, reasonable, assumptions. Reasonable assumptions. All right. If I decide I'm not going to go by contours, I can decide that, okay, carry on, use triangular or triangulated irregular networks. So triangle faces. So that will mean I will simply start drawing, triangles, and then the intersection of these, the edges, so I have only triangles. I cover the whole area. Then I start assigning values to the face of the triangle. Okay, so this triangle will receive a certain color value based on the values of the points, because the points are not forming the intersection of all these triangles. So the value of the face assigned to the face then relates to the values of the sample points. Are you with me? Right. When I'm done, I'll start looking at something looking like a terrain. Wow, that's beautiful. But just that it will be dipping, as if you can walk on the surface. Cartoons, start thinking cartoons. Is that okay? All right. So that is how it's done. It has to be based on real data. All right. So rasters, tints, regular array, and then lines can be used to represent surfaces. All right. So it is possible, okay, to actually have the software do a whole lot for you when it comes to surfaces. All right, so we can have slope, like I said, we can have aspects, okay? We can create density surfaces. Can you imagine that? Density surfaces. They will consider the area and then the amount. Okay, density has something to do with area and then the amount. Okay, so we can do that. We can create surfaces using the interpolation tools in software. All right, an example is what we are looking at. Okay, so for those who are not following and getting the drifts, look at what is on the board. You will see that we have two layers. In fact, in our tutorial that we are going to do, you will appreciate this more. For now, take the theory, knowing very well that I won't leave you without doing the practical. So look at this one. You see that the point, there are so many points with values associated with them. 184, 272, 392, 466, etc. Okay, and then you can see the green colored, picture behind it. Okay, this green graphic behind the numbers. Okay, now that is a representation of the surface. Remember, the definition of a surface is a phenomenon which has values at every point across its extent. So if it's a surface, then everywhere you put your hand, close your eyes, put your hand on, you should find the value there. Look at the green representation or rendering, and you realize that everywhere there is some value of green, except that some are lighter than others. Okay, and so that is a raster surface. So now this one is not a contour, it's not a tin, all right, and it's not a grid, a regular array of points. So it is what a raster. Please, you have to know that. We have actually put the interpolated value on the right hand side so that you can see. All right. So the interpolated values are these ones. So you can see that the values are getting higher. So there's a value range of 658 to 724, the highest value around here. So 662. 662 is in between 658 and 724. All right. Wait. Okay, something is popping up. IDW, inverse distance weighting, is a method for interpolation. We talk about spline, I talk about a natural neighbor. These are interpolation methods. Okay, wait, let's move on. So we have more here. Okay, so yeah, of course, I think this, I have to take advantage and talk about this. There are different methods of interpolation. There is simple interpolation. Simple interpolation is done in surveying when we need to do contouring. Like, I don't know, the software may not even use that. Okay, that's the advantage of using software. Before computers, then you have to do this simple interpolation between 2 points. But now it's possible to make use of other methods. One of them is the inverse distance weighted interpolation. It yielded the surface on the top. Then at the bottom, we are having the spline. Okay, so the spline is also a method for determining values at known points. Natural neighbors also there. So we talk about them. Let's just go up. Let's look at them a bit. Okay. All right. So they estimate surface values for each cell using the value and then the distance of nearby points. So simple interpolation will not consider neighboring points. So just take 2 points and work out. Are you okay? What is your value? If the value here is 2 and here is 4, what is the value between this point A, which the height there is 2, or the value there is 2, and then this point B, where the value is 4? That is simple interpolation. It doesn't care that there's another value on the side, which is a sample. It doesn't consider that. But these methods, inverse distance weighted and natural neighbor interpolation, considers the neighboring points. Are you okay? All right, now we're also saying that the estimates, the interpolated values for IDW services are a weighted average of the values of a set of nearby points. Weighted, so the influence of nearby points is greater than that of distant points. Okay, so there's a theory in geography that near things tend to look alike. So the closer you are to me, I'm likely to be like you. It's a theory in geography. So what it means is that if I'm interpolating, I should consider values that are closer. But then, okay, it doesn't mean I should throw away the values of the other ones. They should contribute, but their contribution should be less. Are you with me? So we use the concept of weight, okay? Okay, let me write the word weight, because some people's network are bad. So we make use of a weight. So a weight, if you want to understand weight, see, go and ask the examination office how they calculate your GPA, yeah, or a GPA, cumulated GPA. Go and ask them. They apply weight to it, which means that every course has a weight attached to it. All right, the importance of it in respect of your program. All right, wait, talking too much. All right, so surfaces are like that. Now you are looking at a typical surface, doing it with